Atmosphere and ionosphere remote sensing. The Earth's atmosphere and ionosphere, our ceiling, what embraces our planet and allows it to contain life. We have spent many years trying to see beyond it, towards the stars, as if it were nothing else than air. But nowadays we know that many human activities affect or are affected by physical and chemical processes occurring there. But it is very difficult to put sensors over the entire breadth and depth of the atmosphere. Therefore, we need to measure it remotely, without having a direct contact with the medium.
Scientists and engineers have developed optical and radar remote sensing techniques to study the ionosphere and atmosphere of the Earth, both from the ground, pointing to the sky, and from space, carried on spacecraft. These measurements are a key element to study phenomena like the erosion of the ozone layer, the shield that protects us against ultraviolet radiation.
Remote sensing research extends to all levels of the Earth's atmosphere. These atmospheric layers cover an altitude range extending from just above the Earth's surface to about 70 kilometers. Beyond, the atmosphere is extremely faint and atoms disappear in the space. Remote sensors allows us to measure atmospheric gases. Measurements of the total content of ozone have been possible thanks to optical spectrometers in the ultraviolet and visible parts of the spectrum. CO2, methane and water vapor can also be measured with the appropriate sensors. Clouds and rain. With remote sensors, we can achieve improved observations that will allow us to see through the clouds, measuring the amount of water vapor, or the rain rate, from heavy to moderate rain to light rain and ice. Crucial data for weather forecast. Aerosols. To study the climate impact of clouds, aerosol sprays and small particles suspended in the atmosphere, we employ LiDAR to profile their vertical distribution. This helps us to understand better the dynamics and energetics of Earth's atmosphere in support of short-term weather and long-term climate forecasts. Temperature and water vapor. In the same way we see the light of the sun, even before the sun rises or after the sun sets, radio waves also bend when traveling through the atmosphere. This way, the radio signals emitted by the global navigation satellite systems provide continuous so-called signals of opportunity that can be used to infer information on atmospheric temperature and water vapor profiles. The lower atmosphere. Using a SODAR, which is a special sensor that emits sound waves instead of electromagnetic waves, we can measure the thermodynamic structure of the lower layer of the atmosphere and the wind speed at various heights above the ground. As an apprentice weather forecaster, you will have to routinely look at clouds to learn how to classify them and infer what they are telling us. Attending their physical appearance, there are essentially three basic cloud types. Cirrus, which is synonymous with a street cloud. Stratus, which, derived from Latin, translates to a layered cloud. Cumulus, which means heap cloud. Clouds can also be classified according to the height of their bases above the Earth's surface, generating different combinations and names. Now you're prepared to start your career as a forecaster. Good luck!